Welcome back, everyone. This is the final session of our marathon two-day event. I think we've had something about 35 presenters from all around the world. And now we're going to, I believe, California, to Vincent. And he'll be telling us about silicon nanowire technology at 1D batteries. And it's really an interesting journey. So I leave it over to you, Vincent. You have about 20 minutes in total. And as always, we really invite the audience to ask questions as you've done throughout the day. So keep your questions coming. We love those questions. So the stage is yours, and yeah, good luck.
Great. Thank you very much. Well, I'm here beginning my day in California, in Palo Alto. As you can tell by my pronunciation, I'm not a native American. I became American later. I'm Belgian, grew up in Belgium and went to the States. And I'm the CEO of this company called 1D Battery Science. Over the last 3 decades, I built a number of companies. And this one, I've spent most of my time for the last 10 years. So I'm going to try to tell you about it. What is 1D and how do we relate to EV batteries? We have invented, and I would say we being our CTO, Yimin Ju, about 15 years ago, started working on this project with the engineering team, a technology called SINANODE. And SINANODE is basically silicon for batteries. And we call that 1D because it's short-handed for one-dimensional, which is silicon nanowires. Nanowires are tiny little hair of silicon. So in the next 15 minutes, I'll try to tell you a little bit about both the technology and the economics. And why do I try to do that? Because I love technology. I'm a scientist. I'm an engineer by training. But at the end of the day, it has to make sense from the point of view of the cost, and it has to make sense from the point of view of the customers able to adopt that in very large scale. And so I'll try to connect the dots, and hopefully you can then ask me a bunch of questions about it. So if I want to summarize, the silicon that we put on the technology, the silicon nanowires, basically deliver about 3,250 milliamperes per gram of energy storage. It's called specific capacity. And that's about approximately 9 to 10 times the energy storage specific capacity of the EV grade graphite that you find in all of the EVs. Now, what's extraordinary, and most people cannot believe, so I will need to explain a bit, is that the process of developing that silicon and the manufacturing process is extraordinarily efficient. The variable cost is less than $2 per kilowatt hours of specific capacity of the silicon. That is very, very low. It compares to about $7 per kilowatt hours for graphite. So this silicon is cheaper than graphite. Now, EV is all about scale, and I will describe the kind of machine we use, but each of those machines is quite inexpensive and can deliver up to 2 gigawatt hours of anode materials for use in the EV cell factories. Typically, if you're going to make, let's say, 500,000 cars, you're going to need about 20 gigawatt hours. It's about 10 machines. And over the last 10 years, we spent a lot of time and a lot of money making sure that this was well protected. And today we count about 240 granted patents in Europe, in Asia, Korea, Japan, China, and the United States. Our investors are on the slide here. The two that are worth mentioning because they're not pure financial investors, GM Venture, that's General Motor, they came into the capital structure of the company last September and invested, and we're working with them to put the technology into their cars. And the other one is Volta, which is a venture capital firm, but quite unique because all of the founders and partners in this firm have PhD in electrochemistry and 2 decades of working for U.S. Department of Energy and investing in battery technology. So they're not the typical VC. Now, there is many, many attempts that you must have heard about of trying to provide an additive to the anode of EV cell by putting silicon in some various types of porous carbon substrate. And those attempts are presented as new, but it's actually things that we did about 15 years ago. And over the years, our CTO had a better idea than creating a new carbon substrate, and I'll tell you what it is. Now, what you have on the left-hand side is basically the powder that comes out of the process. But what it looks like and what it in fact is that's EV grade graphite. So our substrate, instead of being a carbon substrate that we need to manufacture with our own machine and incur cost, our substrate is provided by our customers, and it's EV grade graphite that is already produced in large quantities, and it's already qualified by the EV cell maker. So, for example, we may receive substrate from the customers that is graphite from POSCO, one of the leaders in anode material. Or some of the new companies in North America are called Nouveau Monde Graphite, which is a natural graphite supplier in Quebec, Canada, or even Syrah, which is located in Louisiana in the United States, and they also make natural graphite. Now, we like those suppliers, not only because they make very good graphite that is already EV grade, but they have offtake agreements. So, for example, Nouveau Monde has an offtake agreement with Panasonic, Syrah has an offtake agreement with Tesla and with LG, and POSCO has a joint venture with GM. And you may have read in the news that GM invested about $600 million in the POSCO joint venture for graphite. And so we are graphite agnostic in the sense that we can work with different graphite, but we take those graphite suppliers very seriously because, in effect, they are our manufacturing partners. They do the hard task of producing 10, 15, 20, 40,000 tons of the graphite. And the graphite can be used as is in these EV cell factories. But when we take that powder and we process it according to the SINANODE manufacturing process, we do something that is quite magical. We add silicon nanowires. And the picture in the middle of the screen is basically showing you a cut of a graphite particle. This one is a commercial graphite powder from Nouveau Monde in Canada, but we have done that with others. And if you cut the particles, what you see is that there are those big pores inside the graphite particles. I must say that we start with uncoated natural graphite. And so the little white hair that you see in the middle of the slides are basically like little extension cord. They are made of silicon, and they are plugged into the graphite surface like an extension cord would be plugged into the plug of a wall. And that's the reason this is plugged this way is because the way we grow those nanowires, in fact, involve a catalyst to make that very fast and very easy. But it results in little roots of silicon being embedded into the graphene layer. Now, what you can see on the slide is that the size of the pore is about, in this case, several micron long, and maybe half a micron or a micron high. And there is many pores like that. And basically, the silicon is there because the saline gas that was used to produce those nanowires was able to get into those pores. And the nanowires grew by decomposition of the saline gas. Saline formula is SiH4, so it's one atom of silicon and four atoms of hydrogen. But when we do this, we end up with a powder that's a composite. There is no inactive material, and the powder comprises of the graphite that was initially qualified by the EV cell maker, enhanced by the silicon nanowires, those little hair in white. And the hair are very, very narrow diameters. Now, the little bar that you see, 100 nanometers, that's about the diameter of the coronavirus. So you can see that the nanowires have a diameter about 20, 25, 30 nanometers. And on the right-hand side, you have actually a picture, a TEM picture of a new invention that we did in the last couple of years. We actually developed a way to apply a surface treatment on both the graphite and the silicon that is extremely thin, doesn't add mass. And that surface treatment increases the cycle life. Why? Because it actually stabilizes the SEI that forms during the formation of the cells when you go into at the end of the manufacturing line. It also has an ability to stick better with the binders, which allows EV cell makers to use much lower binder content. And everybody in the industry is trying to reduce the amount of inactive material. So that's the technology. And what's unique is that, and essentially, we don't have to spend any money making the graphite. We enhance the graphite and we deliver something that is known in terms of shape and quality and impurities that is already known to the EV cell makers. Now, our technology toolbox goes beyond that. And what I will not cover today is that we developed also IP over the last 15 years that deals, for example, with multi-layer anodes or dry electrode coating, etc. And so the resulting set of tools that we provide our customers goes from manufacturing process to enhance the graphite with silicon to designs of anode and cells. And the way we engage with those customers is basically enabling through a joint development agreement to work with their suppliers and their engineering team to optimize the EV cells based on the IP that we bring to the table. Now, an example of that is this 4690 cells. Now, most of the cells that we make, we cannot show because they're under NDA with the companies that we work with. But this cell was actually a cell that we commissioned so that we could show it to various people. And we commissioned it from a small company that you may know in Germany called EAS. And if you're on their website, they describe this. So we're not a cell maker, but we can ship them the powder and they can buy commercial cathode and make the electrodes. The electrodes in the 4690 cells are about 4 meters long, and they're being rolled, the cathode and in the gel and the anode in the jelly roll, and stuffed into the cells. And with only about 10% silicon, we can do more, but with only 10% silicon, we can achieve a reversible capacity in the anode of about 600 milliamperes per gram. What's important is that 600 milliamperes per gram is all active material. It's either silicon and graphite. It doesn't include, the traditional amorphous carbon or the binder, excess binder. So you can make cells with binder content that has less than, let's say, 5% of total inactive material in the anode electrodes. And you can pair that with NMC 811 or NCA, etc. And what you end up with is cells that have a respectable 32 amp hour in that format that are tabless and achieve at a jelly roll about 350 watt hour per kilogram on a liter basis, about 1,000 watt hours per liter. Now, this is not ready to go into EV cell production. This is just a sample that we provide our customers as a proof of concept. An actual EV cell takes more work and more time, and we do that with each of the customers. Now, let me talk a little bit about the manufacturing process. On the left-hand side, you see our CTO, Yimin, and on the middle of the screen, you see the machine we use. And this machine is very interesting because it's actually a machine that is used in the solar cell industry. And if you go to, for example, Longi, which is the largest solar cell maker in China, there is hundreds of those machines. So we have a very low capex because we use something where normally you put solar cell wafers into the processing tube, but in our case, we put a reactor with the catalyzed graphite. And this specific machine is for the pilot production. It has 4 tubes, so it can do about 100 tons per year per machine, which is basically about 340 megawatt hours at 20% silicon, which is what our customer needs for pre-production of battery pack testing and qualification. So to summarize, the process use existing graphite, commercial silane, both are available in large quantities, equipment that is available from multiple suppliers, and produce at the end something that is ready to be used. It's a silicon-enhanced graphite ready to be used in all of the existing EV cell factories. And what's unique is that this increases the value of the graphite while decreasing the cost, because at the end of the day, you have basically less graphite needed per vehicle. You go, for example, from 60 kilogram of graphite to about 20 kilogram of graphite. because the silicon is providing most of the specific capacity. Now, a lot of people don't believe in the cost. So we designed this slide to explain exactly where the costs come from. And you have on the right-hand side, basically how much it costs to deposit the catalyst. We use a copper catalyst to decompose silane, and that costs less than $2 per kilogram of nanowires. And the CVD growth, which includes basically the precursor, the silane, the electricity, the nitrogen, etc., all included, even the yield loss. The two of them together is less than $20 per kilogram of silicon nanowires. And of course, the graphite is the substrate. And at the current reversible capacity that is indicated, that works to a variable cost of less than $2 per kilowatt hours. So we believe today, based on discussion with GM and others, that this is the lowest cost silicon solution in the market. And that's important for people that want to make affordable EVs. They have to increase the range and reduce the size of the battery packs, but they also have to reduce the cost. Otherwise, you cannot make inexpensive EVs. Now, the key of this thing is all about the economics. So what is different from any other silicon solution is first, the carbon substrate exists. It's EV grade graphite. Second, we have a patented process to make a copper catalyst so that we can reduce the amount of energy needed and we can speed up the reaction. And all of the silane is decomposed. At the end of the day, the production is inexpensive because the capex is low. It's less than $1 million per machine in large scale production. At small scale, it's less than $2 million per machine. And all of the hydrogen can be recycled to the silane plant because all the silane is decomposed into silicon. The electrode coating is compatible with dry electrode coating. We have more than 10 years of expertise on that. And for the large scale, we have an interesting business model. We design the pilot facilities and we operate that for our customers so they can do enough quantities without worries. But for the very large scale, we decided to go for a licensing model. And we have large industrial partners that have much better expertise in large scale manufacturing plants and also a lower cost of capital. So our customers don't have to depend on a startup to do, let's say, 10,000 tons, 20,000 tons, 40,000 tons of SINANODE for millions of EVs. And that licensing program is possible because of all the IP we've accumulated over the decades. This is a picture from the sky of the first pilot facility, which is in Moses Lake, Washington. And this is kind of a quick picture of our patent assets. You can see that we have about 240 granted patents all over the world. In Europe, we put that in all of the key countries. So that's it.
Great. Thank you so much for the presentation. So the floor is now open to questions. Usually it takes some time for the questions to come in, so I guess I can ask some questions. So how is the stability of this material when it is added onto the graphite? I think you also mentioned a coating, a very special, very thin coating. But I didn't see data, or maybe I missed it, but I didn't see the data showing the stability.
Yeah, so we today for our customers cycle those EV cells to about 1,000 cycles in half a C or 1C rates and achieve between 70 and 80% capacity retention, depending on the amount of silicon. So I think that this new version, where we have added the special surface treatment, has had a dramatic effect on the capacity retention. And so we present those data to customers under NDAs because it's brand new data and it invariably leads to a lot of question about what is the effect of this special coating. And we're pretty productive because we filed a patent application, but it's not yet published. So we have to be careful. I think that the important part is that you can achieve stability in a number of ways. For example, if you were to do amorphous carbon coating all over the particles, that is stable too, but you increase first cycle loss. And typically, people don't want to do that because they want to have a first cycle efficiency above 92% to reduce the cost of the cathode. The other way that we increase stability is that we make experimental anode electrodes in which we have two layers. The layers with a very high silicon content is directly on top of the current collector. And then on top of that, we put a second layer of lower silicon content and bigger graphite particles that has a greater stability and a greater porosity. And this is quite interesting because this kind of sandwich approach provides an ability to produce high energy density, but also high power density. So we have a number of approaches, but this is the example of two approach, and we work to optimize that with each customer.
Great. But what was the approximate number of cycles you achieved at the?
So if you try to, for example, match silicon oxide, and you take a silicon oxide electrode that has from a commercial supplier that has 10% silicon oxide and and graphite mixed together, and it's in full scale production, we can beat that both in terms of capacity and capacity retention over 1,500 cycles in EV cells. So, you get a lower cost silicon, and you get better cycling and better capacity retention than 10% silicon oxide in EV cells.
Great. So what makes the silane grow into nanowires rather than into other morphologies?
That's a very, very good question. Is when the silane is decomposed by thermal decomposition, it will form all sort of shapes and in the pores of the particles, which is not necessarily ideal because it increases the surface area dramatically. When the silane instead is decomposed by the silane gas encountering those tiny little nanoparticles of copper oxide, immediately the silane decomposes in copper silicide, and the copper oxide basically become supersaturated silicon copper silicide, and then the size of the particle deposit the silicon atoms like layers, and the little copper catalyst grows and is at the tip of the nanowire, and the diameter of the nanowire is set by the diameter of the copper catalyst. And so this is kind of crazy because it happened very quickly. In less than an hour, you can grow, micron size nanowires on hundreds of thousands of nanowires per particles of graphite. And so it's very fast, and they grow in those various ways. Now, we literally make trillions of nanowires in this machine on, 20 kilogram of graphite per batch. And our CTO spent 10 years perfecting that. And now it's simple, but it wasn't simple 10 years ago.
Okay, imagine. So you just hinted at the capacity, and I think in your last slide also you mentioned something about having partners for larger capacity. But one of the questions is what is the capacity or
Manufacturing production.
manufacturing products? Yeah.
Yeah. So in Palo Alto, the machine that we have has a single tube. That machine has a nominal capacity of about 25 tons per year. And we have operated that machine since 2018. And so we perfected the process. But we are limited by the amount of silane we can get in Palo Alto with the permits. What happened in Moses Lake, the machine that I show in these slides, is basically 4 tubes, higher flow of silane, and then faster heating and cooling. And that machine is about 100 tons per year, which is if you put 20% silicon nanowires on the 80% graphite, that's about 340 megawatt hours of anode material per machine. And then there is a larger version of the machine that is used by solar cell makers, where essentially it has 5 tubes. And that larger version, there's about 2 gigawatt hour per machine. But the beauty of it is that there are multiple suppliers and the capex is very low. So we designed the process to use existing machines. That's what's unique.
Understood. How much, what kind of loading of silicon can you achieve? Is there a limit?
Yeah, that's a very good question. So we have done loading, on carbon black, for example, as high as 60%. We on the graphite, we've done loading as high as 35, 40%. But at the end of the day, it's not the percent silicon that matters. It's two things. One is what is the reversible capacity? Because it always makes me laugh when people talk about silicon dominant when they have 60% silicon in an amorphous carbon, because it's really 60% of silicon and 40% of inactive materials. So you basically, on the one hand, if the silicon that is partially used, on the other hand, you put a lot of inactive materials. The second problem is that you get cathode limited. So in practice, all of our customers try to achieve anode capacity somewhere between 500 and 900 milliamperes per gram, and for the next generation. And later on, they may go to higher capacity in the anode. But what they want to do is to do that in a way that makes manufacturing sense. So they want to reduce, binder content to less than 5%. They want to use dry electrode coating. They want to use high calendaring. So, for example, 4 or 5 milliamperes per square centimeter. And they're less interested in pushing the silicon to, let's say, 35 or 40%, and more interested in having 4 or 5 milliamperes per square centimeter in the anode. So calendaring properly, using less binder, than having uniform dispersion of the silicon in the layers, and all of those things come into play.
Great. I guess one last question, and then we have to move on to the next presenter. So the question is, what is the first cycle loss?
So typically the nanowires have a 92% first cycle efficiency, 8% loss, which is about the same as graphite. And we do that regardless of the percent silicon. So if you measure in actual cells, the first cycle loss or the first cycle efficiency with commercial cathode, for example, anywhere from a few percent silicon to 20, 30% silicon, it's flat. So it's 90, 91, 92% first cycle efficiency, which is excellent and does not require any pre-lithiation.
Great. Vincent, thank you so much for joining us. Really appreciate it. Very, very unique technology. And yeah, thank you for answering the questions. Unfortunately, we ran out of time. So if you hang around at the end, maybe some people in the meet the speaker room will come and ask further questions directly. But thank
Okay.
you for joining.